Welcome, everyone. It's my pleasure to introduce Shigenori, who's going to be telling us about the structure of W-algebras in type A. Take it away, Shigenori.
Thank you very much for introductions, and I'm happy to give a talk again in this Rocky Mountain seminar. So today I want to talk about some structures of W-algebras in type A, and my talk is based on my project with Thomas, Justine, and Andy, and I think it will be available on archive in a few weeks. Okay, so let me just start with some a very easy or very basic stuffs. So W-algebras, as you know, is obtained from a more fundamental ones, which is affine vertex algebra, through so-called BRC reductions or quantum Hamiltonian reductions. And what I want to start is here we go. The affine vertex algebra is much more explicit compared with W-algebras in the sense that we have a very present presentations by generators and relations. So you have a basis of affine Lie algebras, which generators coming from just a basis of finite dimensional Lie algebras, and a relation is very clear in that way. And of course, we can just put it into purely countable generators, and of course, something like that. And of course, sometimes W-algebras share this kind of presentations. The most fundamental one is the Virasoro. So again, this coming from Virasoro Lie algebras, and as a VOA generated by one element, and the relations is in this way, which is a bit tricky way of writing in Lambda bracket, but it's equivalent to the usual relations of Virasoro Lie algebra. But if we go on to a general case, not the case anymore, unfortunately. And why is that? Is very simple, because W-algebras is defined as cohomology. So we usually write in this way. And so how this kind of things gives some ambiguity of the presentations. Let's take a closer look at the decompositions of BRC complex itself, which is honest constructions of this cohomology. So you don't have to remember everything, but we have a nice decompositions in two copies, and one side it's just trivial, so we don't have to care about that. Just a second. So this one is just trivial, and the other one looks some fancy semi-direct product of affine vertex algebra, which is a kind of minus Borel and some fermions, which computes cohomology. And from these descriptions, we learn that we have certain filtrations of W-algebras, whose associated gradient is indeed affine vertex algebra, coming from G subalgebra, which is a fixed point by F. So at the level of associated gradient, we have again some nice generators and relations, which coming from affine. But the price to pay is that if we want to upgrade this just isomorphism from associated gradient to honest VOA structures, we need to do some corrections because of the filtrations. And unfortunately, this corrections is not so canonical. And starting with the top component, which is the lowest grading in terms of the good grading on the Lie algebra, we just correct one by one, so that we can cancel the, it goes to the declosed in terms of the BRC differentials. So that's why we don't have the nice presentations in general. But if the grading is very, very small, then we don't need such a corrections. And this is exactly what's happening for minimal nilpotent orbits, So in the SLN case, the nilpotent element is just most of diagonal ones. The grading is very small, and we don't need any collections except for the Virasoro element, so conformal vector. And this is what happens for Virasoro case in general. So in general, we need to do some non-canonical collections, which gives us the ambiguity in the presentations, and that's why it looks so horrible in general. So let me just give you an easy example, which is already appearing in SL4 2+2. So in this case, we have 7 generators, starting with finding the subalgebras, and one Katsuron-Akimoto conformal vector, and another copy of SL2, but the grading is different. And OPE looks in this way. And as you can see, large E and large H and so on has a very complicated OPEs. And we don't know, we have a nice formula for central charge of Katsuron-Makimoto, but it's a kind of some unknown rational functions. So, but in terms of if we take a look in terms of the affine SL2 story, it's still a reasonable set of OPEs. So we say that it's still nice, but what about the patterns behind this kind of OPEs? That's what I want to say today. And fortunately, we have a nice understanding to how it should be organized, at least for type A. So this is the title of on the structures of W-algebra in type A. So yeah, let me give you a quick answer in this case. So this is what I wanted to say. We have a uniformly organized OPE that is present, and for SL4 2+2 case as before, we need to do some localizations, avoiding some finite to many levels. But what we need to, what's nice about these things is that we have actually 2 Virazoros. So previously, Katsuron-Akimoto conformal vectors is just 1, but actually we have 2 Virazoros inside it. And the central charge is exactly the affine coset of Hooke-type W-algebras for 1, and other is Virazoros coming from SL2. So we see some patterns behind this story. But we have plenty of other generators. But in terms of Virazoros and additional Heisenberg, it looks still nicely organized. And how this is nicely organized is formulated in the next conjecture. So let's take orbitally nilpotent element in type A, and which is parameterized partitions, and we put it into Hooke type for each. Okay, and then W algebra in general is Hooke type reductions applied several times to affine vertex algebra. That's why we have 2 central charge in the previous case, which coming from the Hooke type W algebras. So indeed, what we are presenting we are conjecture is that it goes for the VOA full structures. And so we can ask that these 2 BRST reductions are the same or not. And our conjecture is that it's the same if we restrict to the casual-rustic categories. So like all the Weil modules and so on. And the main result of the day is that we checked the first coincidence up to SL5. So for example, in the previous case that I presented, 2 partitions is 2 reductions starting with 1, 1, 2, and we have SL2 inside it, so we take another BRC reduction to land on the 2, 2 partition. And the second one is much more harder, and we check that it agrees at the level of characters in full generalities. So we are very confident about these 2 conjectures, and the main result is it's indeed the case up to some evidence. Okay, so this is a kind of purely mathematical way of presenting what I wanted to say today. And as you see from the abstract, I say quite different things. So, and let me explain why such a fancy abstract boils down to this kind of very natural VOA language. So I want to present some explanation from physics. So the starting point, or maybe you know about Hooke-type W-algebras coming from certain physics setups, which is found by Gayoton and Lapchak in the general settings. They call it vertex algebras at the corner in their paper. So the upshot or the summary is that they consider certain 4-dimensional gauge theory. We have some boundaries in 3D and some corners in 2D, and 2D CFT appears in this corner, and we have a VOA corresponding to these physics setups. And this, what VOA we get is that affine coset of Hooke-type W superalgebras. And that's how we are so into this type of W-algebras, and this generalizing Feynman-Frankel type duality and so on, and which gives us a more fancy applications to representation theory of Hooke-type W superalgebras. For example, n equal 2 superconformal algebras, the representation theory can be understood in this way. And actually, in physics community, we have several papers after that. So the most important one for my talk today is Prochaska-Lapchak's algebra, which is a generalizations of this vertex algebra at the corner, and they associate some VOA for so-called PQ waves of interfaces. Let me just give you such a diagram. And so it's a kind of a joint of many trivalent graphs, and by using some gauge groups. And because if you take one corner, then it looks like previous settings. What they say is that the VOA that we have in the end is extensions of many vertex algebras at the corner, and they argue that it should be a affine coset of iterated reductions. So from their settings, what we conjecture is that this waves of W-algebras is indeed a affine coset of a general type A W-algebra. So that's why I presented my abstract in that way. Okay, so this is a physics understandings. Our mathematical understanding is the reductions many times gives us type A W-algebra in general. Okay, so the important thing is to relate these W-algebras is finding nice OPEs. That's how we started today. And so in practice, we need to know how. And it's not so difficult if we go back to the BRC complex. And let me just give you one example by using 2 plus 3 in affine SL5. So we have this kind of strong generators. And how we see it, that we write Young tableaus of these partitions, and we will say that for each rows we have a canonically attached W-algebra, a subalgebra inside it. So J1 is Heisenberg, and L1, L2 is Virasoro, and W3 is the conformal weight 3 generators in the and is W infinity algebra. So how we see is that for each column rows, we have some W infinity algebra shadows, which gives us a nice subalgebra of general W algebra in type A. So how to do that is very important to start with Virasoro, because Virasoro is a kind of idempotent of these vertex algebras, which distinguish what Heisenberg is nice, and conformal weight 3 generators are nice, and what module type extension should be. So as a very, very concrete exercise is find all the possible Virasoro vectors realized in these kernels of BRCD complex. So it's just solving 2-degree polynomials, and we get we take the maximal set of Virasoro, which commute to each other. And in this setting, we have 3 of them, L1 and L2 that I promised, and also, of course, coming from Heisenberg. And then we just find out, use it as a projectors to find another generators in this way. Then we will get a nice organized OPE. So this is how we should organize OPEs to relate W-algebras. And let's go on to how we get the isomorphism in practice. So started with nice OPEs, we want to finish proving isomorphism between iterated reductions and honest W-algebra. So let me do two case, which we started with today. And nice OPEs actually say that we have a nice subalgebra. One side is SL2 and Heisenberg, and the shadow of W infinity algebra. And 2 case, we find Virasoro, and again a shadow of W infinity algebras and Heisenberg. And all these things are related perfectly, like the shadows of the W infinity algebras completely matches at the level of parameters, and the levels of the Heisenberg completely agrees, and Virasoro and affine SL2, their level agrees. So we have a good chance to relate these 2 algebras. And the technology to literally connect them is the inverse Hamiltonian reductions, introduced originally by Semikhatov and used later by Adamovich for representation theory, which says that affine SL2 actually embeds into Virasoro times some free field algebra. And this free field algebra coming from chiral differential operators, but just please think it as just a certain nice subalgebra of rank 2 lattice vertex algebra. So we have a certain embedding by using this CDO in the middle column. So just we extend it to the full algebra by using OPEs. So this is a kind of things that we can naturally guess. And to do so, we just check by hand all the OPEs. And after that, we just take the BRC reduction of this embedding to get the desired result. So this is how we proved case by case in low ranks. So as you see from this proof, these 2 W-algebras has a very close ties. So like one way to say is that we have embedding as reduction by stages in the first line, and we can also characterize this Fock type W algebra by using inverse Hamiltonian reductions. And there is a certain SL2 invariant vector space. And this is how we reconstruct Fock type W algebras. And in the physics settings, 2 to W algebra corresponding to this PQ webs of diagram. And the corresponding statement is that a fine coset of Fock type W algebras here, Virasoro in the low, in the red corner, and Heisenberg conformally embeds into 2 to W algebra. So we are happy that it actually recovers what physics expect and what literally have as a mathematical statement in W algebras. So this is a kind of general setups, but actually we found that it's really nice for rational case. So Fock type, a fine coset of Fock type is a kind of building blocks appearing at each corner. And what I want to say is that in the rational case, it's boils down to minimal series principal W algebra. So as you know, we have some rationality results for type A W algebra, which is called exceptional W algebra. So if we start with admissible levels, admissible level is exactly these rational levels. And if we pick up an nilpotent element wisely, then the simple W algebra will be rational. And an easy way to write is almost rectangular by using a Q as many as possible. This is how we get the nilpotent element, and we get exceptional W algebra. And actually, Fock type W algebra at these levels have a very fancy feature. So this is indeed extensions of principal W algebra in the minimal series, and again admissible affine vertex algebras and lattice VOA actually. So it's a kind of already quite close to the rationality at the level of Fock type W algebras. And we can iterate the BRC reduction for admissible affine VOA again to find many minimal series W algebras in the end. So we checked by hand because we have relations of these two W algebras up to SL5, and because all the relevant W algebras are all rational, this gives us a new proof of rationality of exceptional W algebras. And so next one is what is a branching rule in terms of this subalgebra. And we conjecture and checked in one example is that it is a kind of version of level rank duality if partition is length 2. So level rank duality states a certain mutually embedding, commuting embedding of SLN level M and level rank are switched into a lattice vertex superalgebras. And we have notions of abelian 3-cycle twist to change these affines, etc. And this data completely matching into our W algebra settings. So these two are kind of cousins in terms of tensor category picture. So my the question that captures my mind is that we should have a multi-component generalizations of this level rank duality in the affine setting, which describes a branching rule for this exceptional W algebras. And indeed, this should give us complete classifications of exceptional W algebra in type A and so on. So it's also a very nice thing to see. And I don't know any answer, no clue. So please let me know if you know something of, for example, height 2, length 3, for example. Yeah, so this is a kind of a new problem appearing in the very classic settings, but I think nobody knows the explicit answer. Okay, so this is some nice things that we found in the rational case. Let me go to some irrational case. And I want to discuss about collapsing, so-called collapsing levels. That is a kind of nice levels for irrational settings. So let me give a definition for this notion. And for that, I want to recall that W-algebras have global forms. That is, actually we can define it into the over polynomial rings, whose specializations gives us the levels, and we have uniform strong generators over this polynomial ring and specialize it to our levels, then we get our strong generators. So this is a notion of global forms. And W-algebras are simple for generic levels. So these strong generators are indeed the minimal set of strong generators that we have for generic levels. So collapsing is easy. It's not the case in the simple quotient. So some strong generators drops away under the simple quotient. And so this is kind of very naive, straightforward definitions, but its root is very old, and this coming from exceptional conformal embeddings between affine vertex algebras. Like Frankel-Katz constructions gives us free field realizations of affine SLN at level 1. In this case, conformal vectors coming from Heisenberg's. So this means that Heisenberg coset Virasoro disappears in these specializations. So this, in this case, I want to say it's a vertex algebraic generalizations where how collapsing level appears in the history. So more motivations I should put because it's too naive to think about it. So actually, it's nice for representation theory, which is a recent, maybe 5 years ago by Drazen, Katz, Fraser, Parson, Papi, says that if we, so basically we can prove semi-simplicity of casual-linguistic category inductively. So the important input there is that minimal W algebra is collapsing. Then if the smaller vertex affine real algebra is semi-simple, then we have the semi-simplicity for the original affine vertex algebra. And actually, in this way, they prove the semi-simplicity for type B and D at very fancy levels out of admissible levels. And indeed, out of admissible levels, we don't have much technologies to understand the representation theory. And this is more or less a unique way to do that. And that's why it is so important. Another way to say is that it's coming from geometry. For admissible levels, we can write down the associated variety as nilpotent through size, which is purely, which has studied very much. And so this is examples of the collapsing levels, but it is a VOA upgrade of the coincidence of nilpotent through sizes. So this way, we have upgrades in terms of W algebras of some classical geometry, and which is studied by Arakawa, Van Ekelen, and Moho. So it's also a nice root from geometry. And another one is that we still have some application to the fusion rules. So maybe if you study some fusion rules of W-algebras, you find two affine fusions. We have tensor product decompositions. As you see, Virasoro, we have cut tables, left horizontal and vertical lines. These two gives us SL2 fusion rules, and tensor product gives us the total fusion rules. So this kind of things appears in general, and usually we don't find one copy coming from admissible affine, where we can take the BRC reductions, and which is easy. But the remaining things is usually a mess, and we don't have any clue to understand it. But actually, collapsing levels gives a very precise answer for this. So basically, this tensor product decomposition coming from the choice of the numerators and denominators, and the collapsing level usually happens the numerator small as possible. And what I find with Jethro is that very complicated E8 subregular, we have a collapsing to principal W algebra of G2, where the fusion rules can be described quite easily. So in this way, a kind of building block to understand the fusions is obtained from collapsing levels, which is very hard to prove, but this is a kind of a philosophy that we can learn from examples. So that's why collapsing levels is important in many ways. So let's apply to think about the collapsing levels in our settings. And as you know, as I presented, it's very naive notion. Just some strong generators go away under the simple quotient. So we just compute the Shapovalov form and see which is when it degenerates. So just detecting all the possible ideals. So like SL5 2+3 case, we have 5 conformal weights appearing in the strong generators, and we compute the Shapovalov form at these conformal weights. And literally, we find this kind of complicated forms, and we just take the zeros, and we find 7 levels, which should be interesting. And we compute what is singular vectors and so on. And so, for example, 4 cases out of 7 cases, we find this kind of things. So one case, it's just going to trivial, which is already known. And sometimes it goes to Virasoro out of minimal series. And the other 2 cases is a bit funny that because I put. This coming from singlet algebras or Fagin-Tupnin algebras. So I will give you the definitions in seconds, but what I wanted to say is that collapsing levels, singlet type algebras is a kind of building blocks. This is a message that we got from case study. So let me give you the definitions. And the most general definitions that I found by myself, and we use the Wakimoto realizations of W algebras, and we take the lattice extensions for the free field. And then we have Borel group automorphisms on this Wakimoto realizations, which gives us equivalent bundle constructions over the Flach variety, like here. And Fagin-Tupnin algebras is global sections. And we have another definitions obtained by Dillon and Gatesbury. And how it helps to the singlet type algebras is that this algebra has a nice decompositions in terms of bimodule structures of the W algebra that we started with, and also the global symmetry coming from the global sections. And we have a nice decompositions. And in the SL2 case, it decomposes into just a while modules and just finite dimensional representations, and Virasoro case, it's just a BRC reductions. And the Virasoro, singlet algebra is just a restriction to the weight zero subspace. Because GSL2 acts as an automorphism, this is a simple vertex subalgebra. And this is how to find the singlet algebras in general. Okay, so that's how. So this singlet algebra, I would say, it's a building block for collapsing levels, and we find some natural isomorphism between W-algebras themselves, which is just available at these levels. But what's funny is that under this isomorphism, singlet algebras is a key features that, how to say, make two hands gripped. So 2 case and SL2 at special levels are both decomposing into nicely in terms of singlet algebras. And it is a very common feature that we find in this case study. So maybe it's nice to compare the representation theory, which is the same because all these W-algebras are the same, but written completely different language coming from SL4, SL2, and Feigen-Tupony algebras. So it's, I think, very interesting to compare what the natural dictionary connecting these three. And we have more singlet algebras in other ways. Sometimes we have 2 singlets inside it. And I think that it's coming from the height of the nilpotent element is 2. So we don't know why, but yeah, this is the kind of thing that we find. And we want to know what's going on in general. And yes, it's nice that some of you study further examples to feel the pattern. And more example is hook type up to SL5 again. And what's funny is that to take these decompositions, we usually find very, very special free field realizations available at these levels. So like SL5 3+2, at these special levels, we have these free field realizations. So associated variety, which is not described because it's not admissible, nice admissible level here. But it should be very interesting. And indeed, quite recently, physics people, Koman, Shin, Yamazaki, Zo, introduced quiver vertex algebras, extending the chiralizing the extended Higgs branches. And this gives us chiralizations of a lot of quiver varieties. And I expect that, and there are many, many clues that they actually give a new presentations of singlet algebras at specific parameters. So I hope that this kind of Higgs branches constructions gives us our associated variety, which is very fun to see, I guess. So this is a summary of and comments that we have presented. So this is the main conjectures, and this is the main message of the talk today. So general type A W algebra can be obtained by Fook type reductions, and this procedures works for at the level of representations. Small ranks we checked. Building blocks for exceptional case is principal W algebras, and for the collapsing levels, it's singlet type algebras. And so this is a kind of comment that I will present now. Is it seems that we have a finite analog for this story, and it is based on the result by Ivan Lozev, calling the decomposition theorem of finite W algebras. From that pictures, this kind of iterated reduction is quite clear. And Ivan and his former students seem to writing a paper now. And Naoki and Tibor are also working this kind of things from some geometric aspects. And yeah, that's a kind of finite analog. But also what's funny is that we have a number theoretic counterparts available in the literature. So we have so it's a kind of more Lagrange philosophy. And there is a description of so-called generalized Poitaka models, which is a number theoretic analog of W-algebras. And they have some nice iterated procedures to find in general. And the presentations they give is completely the same as ours. So I think we just found some VOA analogy of this number theoretic result, which goes on to the mathematical physics side, coming from the boundary conditions. So it's a kind of, yes, completing the Rosetta Stones of Edward Frankel in Lagrange philosophy. So I'm also excited about this finding. Okay, so we also have some nice perspective that we can learn from this setup. And the most important one is maybe the rationality of type A W superalgebra, which is very important in VOA community. So the setup is that we consider these two PQFs, and it has some special names. And as you can see, it's just we can obtain one from the other by flipping this diagram. That's why we have some nice connections. And this gives us a generalized Feigin-Frankel type duality, connecting principal W superalgebras and Hooke type W algebras. And what's nice about it is that, as you know, I said that in nice levels, Hooke type W algebras is very close to the rationals. Like it has minimal principal W algebras and admissible affines and lattice VOA inside it. And actually, we can basically deduce that in such a level, principal W superalgebra is indeed rational and C2 cofinite. So this generalizing the principal W algebras of SLN/1 that I proved with Thomas and Naoki, and this is a much huge generalizations of this rationality result. And I think this conjecture is quite new and only available from these pictures, and we are confident about it, and we should prove it because this is a kind of a fundamental problem in VOA community. Okay, so I still have some 15 minutes, so let me just say a little bit about it's also nice to some applications to admissible levels affine VOAs. So as you know, admissible representations is introduced by Katz and Wakimoto to generalize integral representations, saying preserving the modularity of their characters. And kind of easy way to say is that we have the integrability for affine subalgebras, but the parameter of these get to be Q or something like that. And the modularity we can check by hand because we have the character formula. But maybe for VOA perspectives, it's coming from the rationality of W algebras by using Joule's result. So why is that? Is that admissible representations is indeed a casualistic category object at these levels, and BRST reductions gives us W algebra modules, which is rational. So, and we have a very concise procedure to relate these two Q characters. That's why modularity for W-algebra should responsible for the modularities of admissible affine VOA modules. So casualistic category has a braided tensor structures, but it doesn't. This BRC reduction doesn't recover all the W-algebra modules. Like a Virasoro, we just get one copy of affine SL2. To get all the W-algebra modules, we need to start with bigger representations. And the naive guess is just admissible representations, but it shouldn't be the case because it's not a braided tensor category in examples. So we need to work much bigger representations, or we need to do some variants. This is noticed by many years ago by Drazen, Redoubt, and recently Tomoyuki, Thomas, and Kazuya Kawasetsu wrote a paper on affine SL2 weight module categories, which has a braided tensor category by Thomas recently, which should be responsible for this phenomenon. But I think, so let me just present the result with Justine, which is very easy to see. So exceptional admissible levels for type B subregular, we find we can classify all the simple modules, and we can get such a modules from spectral flow twist of casualistic categories. So this extends the honest casualistic categories. We should have a braided tensor structures. So this is a kind of bigger representations categories that we should think about in general. Okay, so how we should get such a representation is general. And inverse Hamiltonian reductions is invented or studied in these directions. Actually, the universal embeddings descend to the simple quotient, except for rational points, integer points. And this is very important because if we consider all the admissible levels, which is integer or not integers, in both cases, we have rational C2 cofinite VOA in this embedding. So the integer part affine SL2 does the job. If it's fractional, we have the minimal Virasoro models. So in this embedding, important thing is that always we have some rational VOA. And simple module for this admissible affine has been obtained or studied by induced module from these bigger ones. And we have some nice modularity result, and we can classify the simple modules, and which is called Redoubt-Wood standard module program, and studied much further by Kawasetsu and Redoubt later. So for example, we start with casualistic category, which is very nicely shaped, but we have category O modules, sometimes appearing at admissible levels, but more wide representations, or the spectral flow twist, and so on and so forth. That's how we these inverse Hamiltonian reductions helps us to understand, to get the bigger representations. And actually, these pictures meet our picture. So meaning that, so as you said, stressed admissible affine, we always relate it to rational C2 cofinite VOA if we consider all the W-algebras. And reduction by stages exactly gives these settings. So this is a SL6 picture, and we have plenty of W-algebras, and Q1 to Q equal to 1, 2, 3, 4, 5, etc. Is a denominator that we need to care about for all the admissible levels. But we can find always rational W-algebras corresponding to these partitions at the end. And reduction by stages gives us a connection one by one of the W-algebras going in this way for level 2, q equal 2, and this is q equals 3, and so on and so forth. So, and as our proof says that we can just invert these procedures. So this means that we can get quite large categories of affine admissibles by using rational W-algebras times many free field algebras. So we should get a nice representation category which is responsible for W-algebras. Okay, thank you so much.
Thank you so much, Shigenori. Thank you so much for the wonderful talk. Let me stop the recording.
Thanks.